So I assume you all can hear me. If not, speak up. And do feel free to interrupt me at any time. No need to raise your hand or anything. Just speak up in Zoom. Or Stephen, if someone locally wants to say something, please interrupt me. I like interactive presentations, but that's not something that needs to be recorded. This is something that is for you all. So let's keep it interactive. So Roland mentioned earlier that the driver for Cactus has several important infrastructure tasks to do. And the driver in Cactus handles, in the case of Carpet, adaptive mesh refinement. I'll have a slide on that, what that means later on. But it's an important discretization method that makes simulations much more efficient because you can put the solution where you want. It handles the parallelization. Roland mentioned there's MPI when you want to run on multiple compute nodes. There is OpenMP for multi-threading and we can GPUs. The driver handles the load balancing and handles the input-output, writing large files. All of that can be very time consuming. And since these are features provided by the driver, other people can write physics downs and then just make use of that. And CarpetX also offers, and that is, I think, one of the most important points of CarpetX, Steve will agree with here, correctness checks. Because if you have a tool like the Einstein Toolkit, it's a huge, complicated code. And no single person has actually written or is expert in all bits of the Einstein Toolkit. And that means when you use it, it's difficult to debug to make sure that you use everything correctly. And it's not just difficult to debug, it's also difficult to actually know whether you made a mistake, whether you need to debug something. So we added a host of new features that catch, for example, uninitialized breakpoints, variables that you forgot to set, or things that are calculated accidentally in the wrong order, and that removes a large source of mistakes. And it's unfortunately still a bit complicated in the current Einstein Toolkit. I see some messages in the chat. I'm just going to ignore them since no one is speaking up. Now, I noticed that Zoom has nice poll features and I've never used them. And since I'm not here locally, I have no feeling for the audience, who you are, what your background is. So I'm going to ask you one question and I want you to answer it. Locally, Steve, you can tally the responses. And in the presentation, if you're calling in by Zoom, there is this one feedback button. What's it called? Reactions? Is it reactions? Yes. And if you go to the reactions button on Zoom, you see a yes and a no. It's a green check mark and a red cross, yes and no. So here is my questions to all my audience, including the expert people. Have you used the Einstein Toolkit before? Please push either yes or no on Zoom, or Steve, please tally the responses locally.
For whatever reason, Zoom isn't working on my machine.
Okay, yeah, you can just tell me what the number is here. And I wonder whether I get some kind of tally here or not. I guess I just get individual things.
I see green check marks and red X's coming out on the right.
Okay, since I'm sharing my screen, I can't actually get a big overview. So Steve or someone else who's on
see
Zoom,
more. I see more green.
5 crosses right now. It's moving up.
Okay, let's give people 10 or 20 more seconds to find that button. So on Zoom, you go to reactions, and then in reactions, you either push green for yes, red for no. Have you used the Einstein Toolkit before is the question. Right now, I sound as if I was holding a pub quiz, so that getting a bit boring. That's probably going to be the only question. People typing the answer in. No, 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 no. Okay, there are 5 more no's. And locally, Steve, show of hands, what happened there?
How many people?
Okay. Are we raising for yes or raising for no?
We'll be raising for yes. There's a bunch. I can't count them.
Okay. Thank you. A bunch, which way? Yes or no?
Yes, a bunch for yes. Most of them, I would say.
Okay, most of the locals have used the Einstein Toolkit before. And in the Zoom chat, I got a bunch no's. And in the other that are tallying? Joseph,
Yeah.
you did that earlier. Can I have another number from you?
Probably 50-50 at this point.
Okay. Okay. A mixed audience. Very good. Very good. That makes my task not easier. So let's go in the slow pace where I, in the beginning, assume that you haven't used the Einstein Toolkit before. And in the second half of the talk, I kind of assume that you might have used it before. And I'm sure there'll be interactive sessions in the end where everything becomes more clear. So I'm moving on to the next slide. Click. Does it work? Yes. So I was going to discuss adaptive mesh refinement. I assume you are familiar with finite differencing or finite volumes, methods to discretize partial differential equation that you want to solve. So here we have 3 levels of mesh refinement. The simulation domain is a square, the black square here. Say, can people see the mouse pointer? I assume yes. No one's
Yes.
answering. Okay, you can see it. And then let's assume we need a higher resolution in this region of the domain and this region of the domain. So we put some these blue grids with a higher resolution in there and some red grids with the even higher resolution in there. And of course, the advantage of adaptive mesh refinement is that we don't have any higher resolution here. So if we were to cover the full domain with this fine red grid, obviously you'd need probably, I don't know, 10 times as many grid points as this. You can kind of assume that if you use a mesh refinement setup like this, the simulation runs 10 times as fast as if you were using a uniform grid that uses the fine grid everywhere. That's 2D and 3D, of course, if you refine only near a neutron star or black hole, there's a lot of empty space around it, but you don't need resolution. So adaptive mesh refinement is crucial, and it's widely used in astrophysics for hydrodynamics calculations. And this adaptive mesh refinement is provided by the driver. And I forgot to mention, we're using a software package called AMREX or AMRX, which means adaptive mesh refinement for exascale. And AMREX is part of the ECP, the Exascale computing project that's funded by the Department of Energy in the US. And that means that AMREX and many other software packages actually have paid software developers, making sure the software is working, that the software is adapted to modern HPC architectures as they come along, and that the software packages play nicely with each other and are relatively easy to use. And we very much benefit from that for the Einstein Toolkit, although the Einstein Toolkit is not part of the ECP project. Parallelization, Roland mentioned ghost zones. If you have mesh refinement and we want to run the calculation on different nodes, and let's say we have 2 grids, a red grid and a green grid of one level, that is a cursor level around here, then we can just put the red grid on one compute node and the green grid on another compute node, and that is an easy way to split them. Or we have GPUs. The red grid goes on one GPU and the green grid goes on another GPU. That's also handled by CarpetX. And if you're using multiple threads, or what the GPU would internally be doing with multiple blocks, if you're familiar with GPU computing, then each of these grids would be split up like this. So this would be suitable for a computer with 2 nodes, and each node has 4 cores. So my laptop has 8 cores, so you would have even more of these tiles available, or in 3D, it's kind of natural. And you want to make these tiles as compact, as squarish, circulish as possible. Of course, in finite difference, if you want to calculate for one grid point, you need access to data on neighboring grid points. And the more of these neighboring grid points are located on the same thread, the same tile, or the same node, the faster, the more efficient the calculation goes. Exactly how to split the domain and how to distribute it onto the nodes is called load balancing, because you want to make sure that each node has about the same amount of work. Because if one node has twice as much work as the other, then the other node has just to wait idly while one of the other nodes is busy. So node balancing is very difficult because otherwise the simulation would not run efficiently. Load balancing is also something that's handled by the driver for the AMREX infrastructure. Ghost zones is something that Roland already explained. He explained it in 1D. In 2D, it looks like this. Just going to go over it again. So these black squares here are the actual data that we want. And then if we want, say, a finite differencing derivative here, we need information from neighboring points. And that means we need to add a layer of ghost points around here. These ghost points here on the outside, there's no other grid. So we probably get them from the next coarser grid via interpolation and adaptive mesh refinement. That is called prolongation. And so there are various interpolation prolongation operators provided with CarpetX. And it's also handled automatically by the infrastructure. But you still need to say when you want that interpolation to happen. Probably right after you calculated everything in the material, then you say you want that, set the boundary points. And here in this overlap region, actually, it's actually incorrect. These 2 points here should not be part of the overlap region. That means the ghost points of one grid, they overlap the interior of the other grid. You see the shaded region here. So the blue data here are copied from the underlying orange data here. And the orange data here are copied from the underlying blue data here. This is about ghost zones, prolongation, and synchronization. And CarpetX, one of the new features of CarpetX is that it does not only handle cell center data, but you can have staggered grids. So for example, if you have conserved quantity, so the mass in hydrodynamics, and you store the mass, the amount of matter, number of baryons in a coarse cell here, and then you refine it, you split it into 4 subcells here, then it's quite easy to split, right? You take the mass and the coarse cell, you split it into 4. Each of the fine cells gets 1/4. But if you have a quantity that is not a conserved quantity, it's more like a pointwise quantity. For example, the electric potential or something. The electric potential would be more naturally stored at the vertex here. And then you also store it at the vertex at the fine grid. Actually, I don't have an example here, so let's do something else. If you do hydrodynamics and you store the amount of matter in a fine cell and you update, then you want to conserve things. And the way you do that is a flux conservative scheme. You calculate the flux through the phase between cells. So that's one cell, that's another cell, and that's the phase between cells. I should use this grid here. So you calculate the amount of flux through that phase. And then whatever you take out from one cell, you add to the other cell. That would be a flux conservative scheme. And for that, the fluxes need to be located on the phases, not at the cell centers. And here, that is an example of a phase-centered grid. These are X phases. A grid that's centered in the Y direction would look equivalently. If you look at the points here, they're in the centers of the cells, and here then the faces of the cells. If you count here from left to right, they're kind of 10 points, 5 triangles, and 5 diamonds. And if you count from here to here, you have 11, not just 10, because there's kind of one more face than other things. So in a hydro scheme, what you would want to do, first you calculate the fluxes, and then you exchange the fluxes here with a ghost zone exchange to make sure that all the faces have consistent fluxes, and then you update the information in the cell center. And so
you may have already explained this earlier. Do you mind explaining why the different shapes, like why there are like 4 separate, you split up each point into like 4 different squares?
Oh, here, yeah, that was this one. This was the parallelization scheme that is called tiling. So each of these grids here is stored as essentially one big 3D Fortran array. I mean, we're not using Fortran, but the Fortran memory layout is still the most efficient one. And then we might want to use 4 threads to work on this. And these 4 cores, they actually share one socket on the hardware. They share one memory. So we put the 3D array into memory, and the 4 cores access the same memory, and each core works on one subsection of this. This is called tiling, and this is an efficient OpenMP parallelization. And yeah, these images here, I just took them from the AMREX documentation. I should have added that here as well. Sorry, let me just, how does that work? Copy that over to the next slide. Sorry. How do I? These are taken from the AMREX documentation, so they don't quite match what I want to do. But AMREX is well documented, it's taken from the website. So just interpolate, so just explaining the various centering here, I wouldn't need to put the tiling on that. It's maybe a bit more confusing in this context. Did that answer the question?
Thank you. Yeah.
Okay. Now, having said, giving a brief overview over what the driver does and how CarpetX does it, I want to present the new features of CarpetX. This is why many of the people who are contributing to CarpetX are very excited of it. And this is a bit where I'm dangling the carrot in front of you, as I mentioned earlier, because you are not using CarpetX. I don't know, are they? Steve, they're using Carpet, right? Not CarpetX? Steve is not listening or is muted. I assume the tutorial, yes?
Didn't hear your question.
Oh, the tutorial will be with Carpet, not CarpetX, I assume.
There is, both are provided for. There is a pre-built version of CarpetX as well as a pre-built version of Carpet.
Oh man, yes, that is cool. Okay, yes. Anyway, these are the new features of CarpetX, which is based on AmRex. So let me just go through them. So one of the features is that there are no cell-centered variables and face-centered and edge-centered variables, which allows important algorithmic feature. For example, if there's a mesh refinement boundary, you get exact conservation of mass through the mesh refinement boundary. That is an important feature if you have shocks or discontinuities in hydrodynamics. Refluxing is something that is there, but you're not actually needing it at the moment, because we use a different scheme that's equivalent. And edge-centered variables might be necessary for the magnetic vector potential. And if you use these, then you automatically ensure that the divergence of the magnetic field is zero. Is you calculated it as the curl of A, and then the divergence of a curl is actually zero. I mentioned this to avoid errors in the schedule, the order in which you calculate things. Maybe you forget to do something, forget to synchronize the pressure after calculated. This can now be detected automatically. Applying boundary conditions is much simpler now, because instead of saying that you want to apply a particular boundary condition to a particular variable, for example, the metric should have a directly boundary condition, you just declare in the beginning, oh, the metric always has this boundary condition, and then whenever CarpetX figures out that you need to apply the boundary condition, it does that. You don't need to say when you actually apply it. The support for GPUs and for more efficient multithreading is what gets many people interested in CarpetX. Although I really think this is the most important thing. I should probably make it bold because I like it the most. And then we also have improved parallel scalability. So Carpet scales to, depending on your setup, 1,000 or 10,000 nodes. And CarpetX should scale to about 10 times that. But there is a particular caveat that I'm going to mention later on. And we're also switching from a standard IO format to efficient and standardized file formats. And the advantage of that is that IO is much more efficient. We're using libraries for IO instead of rolling our own IO file format. Now, the status of CarpetX, I mentioned it's a new thing. So the new features I mentioned earlier, they're all working fine. So this is all good, no problems there. Apart from that, I would say it's better quality. It's ready for first production runs. There's a paper that was written with CarpetX, but some small features may be missing. For example, 1 week or 2 weeks ago, Sam ran a binary black hole simulation and it was working fine, but checkpoint restarting of some particular thing was missing. The code aborted because it didn't know how to store the current location of the black hole. So we fixed that, and now it should be working. I actually haven't heard what the next problem is that Sam has encountered, but I hope he's tried the new version of the code. And CarpetX is not yet part of the Einstein Toolkit. It's currently under review. And I hope that it can be released in the fall with the Einstein Toolkit. But one of the big things that doesn't exist yet is a nice tutorial for CarpetX. So if you have used the Einstein Toolkit before, and if you now make the effort to start using CarpetX, then it would be really cool if you could write up your experiences For example, you could tell people, this is what I needed to do to change my code to work with CarpetX and so on. It doesn't have to be nice and polished, but just writing it up would help, because it's very difficult to do that for me because of all the code I'm using. I already converted it to CarpetX, so I might miss something. It would be really good to get help with that. I mentioned that there's a paper out, there's a presentation with GramX by Philip Mister, I believe, in a few days. And yeah, I guess that shows that CarpetX is ready for production use, but you probably want to be collaborating with us so that we can fix the bugs in CarpetX and the missing features that might still be there. This is a dense slide. I was debating whether we want to have it or not. Here, I describe things that CarpetX does different than Carpet. And these are things that might affect you when you use the driver. In an ideal world, you wouldn't notice the changes that we needed to introduce to the Einstein Toolkit in CarpetX, but some of these are just necessary. So, for example, the time integrator in the current Einstein Toolkit, it's a bit complicated to use the time integrator. You need to call certain functions at runtime to register your variables and how to calculate the right-hand side, and that is now all automated. Now, in principle, it's good that it's all automated, but of course, the bad thing is now you need to use the new mechanism to do things. Boundary conditions are handled implicitly, automatically. That's good. But that means if you have an existing code that does the boundary conditions manually, you need to take out that bit of the code to make it handle. The multi-threading is now much more efficient, and that's good. But that means you don't do OpenMP programming yourself. It's all moved into the driver. And if you want to use GPUs, obviously some changes might be necessary because certain kind of code can't run on a GPU. For example, on a GPU, you cannot access global variables. So if you have a code that's a bit unclean, you use something for a global variable here, or you output debug messages on a GPU and so on, that just won't work. You might have to rethink that. Yeah, we're having true self-centering, I don't know. And yeah, the IO format is different. So if you have any visualization tools, you might need to update them because now we're using standard file formats. So all the tools that you might have that use the homegrown format, that they would need to be updated. And that's probably the biggest thing here. It's an algorithmic change. So whenever you write a new code, design a new system, then on one hand, of course, you want to make the new system as big, as complete, as easy to use as possible before it to show it to other people. On the other hand, it's really important to get early feedback from other people, because otherwise you design something and you miss some key ideas, some key requirement, and it doesn't work. And in software engineering, this idea is called the MVP, the minimum viable project. Sorry, minimum viable product. So you want to design something that is useful to others, but does not have all the features that other people want, but still has all the key features. And then you can show it to others and they can give you feedback, and then the project grows in a much better way. And in CarpetX, we decided that subcycling in time is not part of phase 1 of the first release here. So there are two kinds of mesh refinement, with and without subcycling in time. And the idea here is that if you have a fine grid with a high resolution and a coarse grid with a coarse resolution, then in coarse grid, you could technically take much larger time steps because it's a coarse grid. And if you have a refined region near the black hole and a large amount of empty space-time around it, then in that large region of space-time, you have a coarse grid. So in that large region, you can take coarser time steps, and that would reduce the computational requirements very much. And a large part of the domain is a really good thing. And this is called subcycling in time because you take smaller time steps on the finer grid than on the coarser grid. But it is very difficult to implement. And it is very difficult to get correct because making these different time steps match nicely, match in a stable manner that you don't get any problems there is difficult. And we developed some methods over the years, but these methods are kind of expensive. So an estimate is that in the current Einstein Toolkit, if you do use subcycling, about and in some circumstances, about half the computing time is spent just getting this matching to happen correctly. And it's called buffer zones. And that is really bad. So we wanted to throw it out. So we did, but currently we don't have subcycling in time. And these days, of course, I mean, Carpet is kind of 20 years old. People have developed their respective numerical algorithms to do subcycling in time properly, but we have not yet implemented that in CarpetX. So the plan is if people like the current CarpetX, if they find it efficient, if they can program on GPUs and so on, if they like the features, then in the future, we're going to implement that. But it's not part of the first release because we decided it's not part of the MVP, minimum viable product, of phase 1. Oh yeah, right. So yeah, phase 2. Missing in CarpetX, it's the subcycling in time that is not yet implemented. That's probably a feature that most of you who are familiar with the current Einstein Toolkit and Carpet will notice first, because that's the AMR algorithm in Carpet. It does use subcycling, and in fact, you can't switch it off there. The AMREX domain decomposition that's provided by the AMREX library is efficient if you were to use subcycling. Since we don't use subcycling, there's a thing where we could increase our scalability by a factor of 5.
We have a question in the chat. What is subcycling?
Oh, okay. I mentioned that earlier. Let me go back here. So you have so this is the subcycling is part of the adaptive mesh refinement algorithm. So here we have a coarse grid with a coarse resolution, and then finer grids with a finer spatial resolution. And the time step size that you can take in a time integrator is limited by the propagation speed, by the speed of light, and the cell size of the finest grid. On the coarse grid here, if we only had the coarse grid, we could take time steps that are 4 times larger because the grid spacing is 4 times larger. And subcycling means that in this AMR grid, we take different time step sizes on different grids. So we take a small time step size here, twice as large here, and twice as large here. Or put differently, we have a time step here and half the time step size here. That's why it's called subcycling. And again, half the time step size here, kind of subcycling. It's a recursive algorithm. And as I mentioned, this algorithm is complicated, and you need to make sure that things remain consistent across these interfaces where you take different numbers of time steps at the cell faces. And since it's difficult to get correct and it's a complicated algorithm, it's not yet available in CarpetX.
By the way, Erik, you have about 5 minutes left.
Okay, yes, thank you. Okay. In the past few slides of my presentation, I was going to go into some details of CarpetX, how you actually program against CarpetX. I put that in there because I didn't quite know my audience. And given that half of you haven't programmed with the Einstein Toolkit yet, I want to leave that to a different time. It's there in the slides if you want to know it, but we don't need to go into details and exactly how you program the interface with CCL, because you might not even have heard about what interface with CCL is. So going to skip over that. Here's a general description of how you do something, how you write a hydrodynamics code to make it consistent. I mentioned it earlier in words. You need to do this in a hydro code. First, you calculate the fluxes, and the fluxes need to be phase-centered grid functions. And you synchronize the fluxes, and then you use these fluxes to calculate the update terms. And that gives you a flux conservative scheme, even at mesh refinement interfaces. And yeah, just going to skip through that. Multi-threading is the same thing as I mentioned earlier, GPUs. And no, that's also too much detail. Okay. There's one. No, I should not tell another story. I'd rather stop my presentation here and ask whether you have questions.
So are ghost zones just required at the boundaries of like what you're simulating, or do you need to put them also where there's a change in the refinement of the mesh?
Okay, so the ghost zones are automatically added by the driver. And the ghost zones are necessary every time they're kind of one of these 3D Fortran erased ends. And in your question, yes, they're needed at the outer boundary. And yes, they're also needed where the mesh changes. And let me scroll back here to the AMR grid. We would, I mean, all of the 5 of these boxes would need ghost zones. So the overall domain for the boundary conditions, and the blue ones here because the mesh refinement, the mesh spacing changes, and here it's still 2 arrays where they need ghost zones. Actually, maybe there's a better one. Sorry, I'm scrolling through. Here you see where the ghost zones are. Actually, you don't see them on the courses grid. They're also necessary there for boundary conditions. And the boundary condition could be a physical boundary condition, or a Dirichlet boundary condition, or periodicity or something. And they're added automatically.
Okay, thank you.
Any other questions? I can actually see that, yes.
I have a naive question, Eric. It's about multi-threading. I was interested that you mentioned CarpetX is expected to perform better than Carpet. And that's something that we test a little bit, probably you test much better. That we use as a rule of thumb the number of threads to be the number of cores per processor, to a starting point. But then we found that this was not necessarily the optimal regarding speed, and it was not portable, hardware dependent on what we do. So I was wondering if CarpetX is more robust regarding this, or what your test produced.
Yes. So for Carpet, the old infrastructure, the rule of thumb is do not use OpenMP, use MPI where possible. But at some point, you're getting into scaling problems with MPI. So if you use 1,000 MPI processes, then maybe you want to stop there and then use as much OpenMP as possible. So if you run on 10,000 cores, then you would use OpenMP multi-threading. But if you run only on 100 cores, it's probably the fastest to not use any OpenMP. That was the old infrastructure. And the new infrastructure, it's the opposite. If there's a core, sorry, you have a node with 2 processors and each processor has 20 cores, then it's probably reasonable to use 20 OpenMP threads. It might be slightly faster to use only 10 OpenMP threads, but it's not a big difference. So with CarpetX, the rule of thumb is that you want to use close to the number of cores per processors. Now, it's not the number of cores per node, but because a modern core actually is internally something like 3, 4, 8 computers with a fast network in between. So you need to find out how many sockets you have, or whatever they call it these days. And I think a modern AMD hardware might have 8 sockets, and each socket has 8 cores, or whatever they call it, chiplets, blah, blah. And then you would use 8 MPI processors, 1 per socket, and each of them using 8 OpenMP threads. There is still experimentation necessary, but the rule of thumb for CarpetX is that you want to use many threads.
Thank you.
Any other questions? Yes.
I have a quick one. So if I schedule in Carpet, right? If I schedule a routine in global mode,
Yeah.
then I have like looping macros like begin graph level loop, blah blah blah, to access individual grid points.
Eric,
That's
can you hear this
similar-
question?
I can hear the question, yes.
Okay.
Go on.
Are there equivalent macros in CarpetX?
Yes and no, it's not macros. So in CarpetX, we drink the C++ Kool-Aid. It's C++ 17. So there are functions that do that, and you pass lambda expressions to these functions. But yes, they're available. They are in the driver and they're not properly exported. We probably should do that. You can open a feature request for that. And I don't know, it's probably called loop over blocks or something. So the thing that used to be called components in Carpet, now Amrex calls it blocks. So we're calling it blocks as well. And in this picture here, this would be one block and this would be another block. So a block is essentially something that looks like a Fortran array. And you can do that. And yeah, of course, there's the usual thing. You don't want to loop over all blocks. You only want to loop over the blocks that are stored locally in the current MPI process. And if they're using a multi-patch system, which I'll be talk about that tomorrow, how that is going to look like, and you probably want to loop over the patches there as well. But scheduling in CarpetX is much easier because there's no level mode, because we don't do software cycling. But there's local mode and global mode, and the local mode is just a simple loop over global mode. So I have not seen the need to use macros like that, except in special cases, for example, inside the elliptic solver. I did not mention the elliptic solver. There's now an elliptic solver that comes with CarpetX. So if you have an elliptic equation, you can solve it on your AMI infrastructure. I really want to see people use that. So far, only I have used it, and I'm solving the Poisson equation. I mean, of course, why not? It's boring. Sorry, go on.
All right, any other questions?